Okay, so welcome back into another video. So in today's video, we will be evaluating this infinite series, the series from n is equal to 0 up to infinity of 1 divided by 2n squared plus 3n plus 1 multiplied by n factorial. So, okay, let's get started. Let's actually rewrite our denominator. Specifically, we're just going to rewrite the what's in parentheses a little bit differently. So if we focus on that, so we get so starting off with 2n squared plus 3n plus 1. What I can do is I'm actually going to rewrite 3n as terms of 2n plus n. So square plus 2n plus n plus 1. Okay, and then notice that I can factor out 2n. So 2n and then n plus 1, and then we have an n plus 1 here, so it's just multiplied by 1. And then we can actually use our we can unfoil this, so we get that we have binomial factors of 2n plus 1 multiplied by n plus 1. Okay, nice. So therefore, now let's just ignore the n factorial for a second and then just focus on the fraction itself, which is 2n plus 1 and then n plus 1. And then what I can do is let's actually decompose this so we can get some partial fractions. So this is 2n plus 1 plus n plus 1. And then we have to solve for our coefficients a and b. So just use the butterfly method. So, and then we just focus on the numerator. So this is a times n plus 1 plus b times 2n plus 1 equals to 1, which is our numerator. So let's say we plug n is equal to -1. So this is -1 plus 1 is just 0, and then plus b times 2 times -1 is -2 plus 1 is -1 equal to 1. And let me do the other one for so let's see, plus 1, so it's 1/2, or yeah, -1/2. So this means we have a times -1/2 plus 1, and then plus b times so this should be 0 over here, and then that's equal to 1. So we have that a is equal to or right here, what was I meant to say, negative half plus 1 is 1/2. So, and then you just divide the 1/2, so that means a is equal to 2, and then b is equal to it's -1. Okay, so we have our coefficients. So we have 2 divided by 2n plus 1 minus 1 divided by n plus 1. So now that we have the decomposed fraction, so now let's actually multiply the factorial denominator in there. So let's just rewrite our sums again. So this is the infinite series, n is equal to 0, and I'll write this in brackets. So this is 2 divided by 2n plus 1, and then minus 1 divided by n plus 1, then multiplied by 1 divided by n factorial. Using, our distributive properties, we can distribute a 1 over n factorial to both terms, and then, but we can also use our rules of a series that we can actually write this into 2 different series. So this means this is the series, the infinite series, n is equal to 0 of 2n plus 1 multiplied by 1 divided by n factorial, and then minus the series 1 divided by n plus 1 over n factorial. Okay, and then actually I can actually factor out the 2. So I can actually factor out the 2 outside. So this means this will just be a this will be a 1, and then this will be a 2 out here, equals. Okay, nice. Let's actually focus on evaluating this series first. So note that n factorial is actually equal to just n multiplied by n minus 1 multiplied by n minus 2 dot 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 so on 3 times 2 times 1. It can actually be arranged into a product series of n from your index starting from n is equal to 1 and then 1 up to infinity. Okay, so now if we were to multiply the now notice if we were to multiply n plus 1 multiplied by n factorial, this is simply just n plus 1 multiplied by n minus 1 multiplied by n minus 2 and then so forth. So there's actually a precursor term n plus 1, so there's a term before the n, so therefore we can actually rewrite this as n plus 1 factorial. Okay, we can rewrite this as the new infinite series n is equal to from n is equal to 0 to infinity of well, first let me just reiterate and say that this series n plus 1 multiplied by n 1 divided by n factorial, this is just equal to our new infinite series of 1 divided by n plus 1 factorial. Okay, nice. Another thing to note is that our constant e, it's represented in the form of the series of the summation from the infinite series of n is equal to 0 to infinity of 1 divided by n factorial. And let me actually expand this series out. So this is, so we start with n is equal to 0, so 0 factorial is just 1, 1 plus, and then n is equal to 1, so that's 1 plus 1 divided by 2 factorial, which is just 1 over 2, and then plus 1 over 3 factorial, which is just 3 times 2 times 1, so it's 1 over 6, and then so on and so forth. And let's also expand this series out. So we have n is equal to 0, so that means 1 divided by 0 plus 1 factorial, so this is just 1 factorial, it's just 1, then plus n is equal to 1, so 1 divided by 1 plus 1 factorial, so 2 factorial, so it's just 1/2. Okay, and you see we're getting somewhere. We're getting similar terms within the correlations of these two series. So 1 over 6, and then so on and so forth. So notice that these the second, third, and fourth term of our e expansion is equal to this series. So therefore, I can rewrite. Let me say e is equal to 1 plus, and then let me just substitute our second, third, and fourth and onwards term from our e and substitute it with our series of 1 divided by n plus 1 factorial. So n is equal to 0 of 1 divided by n plus 1 factorial. Okay, and then I can just subtract the 1, so therefore this series is just equal to e minus 1. Okay. And that's not the final answer, but that's just our evaluated term, our evaluated series for this one. So I'll just box this in red. And that, let me also draw an arrow. This is our evaluated series for this series in particular. Okay, cool. So now the next thing we need to do is we need to evaluate this series. So, and there's also some facts that we want to use in order to evaluate this this series in particular. So let me write some facts down that we're going to be using to evaluate this. So fact. There's three different tools that we're going to use. So one thing is that the error function of x is simply just equal to 2 divided by the square root of pi multiplied by the integral from 0 to x of e to the negative t squared dt. Okay. Then the next fact I want to use is that the imaginary error function, this is just erf and then I of x is just equal to negative I multiplied by the error function of I times x. And then one more thing I want to use is that now this time e to the x is equal to the specifically its Taylor series is the infinite series from n is equal to 0. Yeah, n is equal to 0 of x to the power n divided by n factorial. So we're going to be using these three definitions to solve this this infinite series here. So going back to the error function that we just defined, so that's what we're going to do. So the error function, we're going to actually replace our e to the negative t squared and express that in terms of the series. So in this case, we're going to let x equals negative t squared and plug negative t squared into here. So this is just, yeah, I can write over here. So error function of x is equal to 2 divided by the square root of pi, and let me just rewrite the definition again one more time just to reiterate, even though it's already written up there. So e to the negative t squared dt, and then simply that's just equal to, so we'll just replace our e to the negative t squared and use this, use it in terms of the series. So this is 2 divided by square root of pi of the integral from 0 to x of this infinite series, well, the Taylor series really, equals 0 of, so this is negative t squared to the n divided by n factorial dt. Okay, and now let's distribute the n, the power n, into here. So this is simply just, so let me just rewrite this again. So pi, and then this is, and I can just use our rules of series and then just move that outside the integral itself, and even including the n factorial. So really, n is being distributed to the powers of both -1 multiplied by t squared. But the -1 is just a constant, so I'll just move that outside. Write the series again. So this is -1 to the n divided by n factorial, and then multiplied by our integral, which is, so this is 2t to the power 2n dt. Great. Okay. Alright, so now the only thing we need to do is just evaluate this integral, so it's pretty self-explanatory from here. You just use the power rule. So tn dt, this is just equal to, so this is add 1 and then divided by that, so this is t to the 2n plus 1 divided by 2n plus 1 divided from 0 to x, and that's simply just, so notice that if you plug 0 for t, then it means the whole term just becomes 0, so that just cancels itself out. So the only thing we just need to just distribute the x. This is just x to the 2n plus 1 divided by 2n plus 1. Okay, now let's actually just distribute our evaluated definite integral. So, okay, so 2 square root of pi, then series 0 of, so this is -1 to the n, then x to the power 2n plus 1 divided by 2n plus 1, and then multiplied by n factorial. Okay, let's see, yep, that's good. And now, now that we have that, now let's actually substitute x equal I. So let me just write. Now substitute I. That means the error function of I is just equal to, so just basically the only thing we need to put x is just I, which is just right over here. 2 to the square root of pi, and then the series 2n plus 1 multiplied by n factorial. Okay, now the next step is going to be interesting here. So there's something we want to observe. So let me actually make a chart on this side here. So now we have that, I'm gonna let n here, we're gonna create a table, and then we have -1n I 2n plus 1. Okay, so let me just write for 0, 1, 2, 3, and then so on. Okay. There we go. That's nice. So now notice that if we were to plug 0 for n is equal to 0, so if we plug 0 for here, so -1 to the 0 power is just 1, and then 2 times 0, 0 plus 1, which is just I, so we get that this is I. And if we now next is to plug n is equal to 1, so this is 2n plus, so 2 plus 1 is 3, so I to the power of 3. And then multiply by -1, so this is negative. Then that means this is actually equal to I. And next is to plug 2, so I 2, and then 5, so that's actually just equal to I. Okay, and then 3, which is 2 to the 3, 6 plus 7, which is I to the 7th power, so that's simply just I cubed, yeah, and then -1, so that's negative, and that will be I as well. And then you keep doing this so on and so forth, and you actually get that no matter as far as you go for n, when n tends to infinity, you're gonna get the result for the numerator is actually just going to be equal to I regardless. So simply, the numerator we can actually just replace with just I, and because I is actually, well, of course it's an imaginary unit, it's still treated as a constant in a sense, so we can actually just move that outside of our series. So this means this is just equal to 2 times I divided by the square root of pi. And then we have our series again, 0, which is just 2n plus 1 n factorial. Now let's actually multiply I to both sides. So just so this way we can cancel this I on the right side of the equation. So that means this is I multiplied by the error function of I, which is equal to I times I is I squared, which is -1. So this is just -2, and then divided by the square root of pi, and series infinity to n is equal to 0 to infinity of 1 divided by 2n plus 1 n factorial. Okay, and now I can just divide -2 divided by pi square root of pi to both sides. So and then we'll just get negative square root of pi divided by 2, and then I f I, and then this just equal to our series. And it's equal to 0, and then 1 divided by 2n plus 1 n factorial. Okay. Now the last thing we want to do is that using the fact that the imaginary error function of x is equal to negative the error function negative I multiplied by the error function of I of x. So notice that there's we have a similar format here. So in this case we let x equals to 1. So this means if we let x equal to 1, so that means this is the and this is also the negative. So this means this will change into a positive. So that way we get over here, this is positive square root of pi divided by 2 multiplied by the imaginary error function of 1. So yeah, that's actually our evaluated infinite series over here. This is just equal to n is equal to 0, and then 1 divided by 2n plus 1 n factorial. Okay, nice. So we have, this is our evaluated, and then let me draw that arrow again a second time. That's for this series. Okay, now all that's left is, now that we have our necessary pieces, now we can just calculate this. So let me rewrite this a second time. So this is 2 times the infinite series of 0 of 1 over n plus 1, and then multiplied by 1 divided by n factorial. So just substitute our pieces. This is 2 times the square root of pi divided by 2 of our imaginary error function at 1, and then minus right here, e minus 1. Okay, and now simplify this out. We get that the final answer is just equal to the square root of pi multiplied by the imaginary error function at 1 minus e plus 1. All right, there you have it. And you can actually use Wolfram Alpha actually to verify this. You should get the same answer. So like so. That's our final answer over there. Reiterate one more time. Therefore, the infinite series from n is equal to 0 to infinity of 1 divided by 2n squared plus 3n plus 1 multiply n factorial is equal to the following over here. Square root of pi multiplied by their imaginary error function at 1 minus e plus 1. And there you have it.